Hello, welcome to my talk. I'm Eleen. I'm a school teacher for mathematics, astronomy, and PE in Germany. Today, I would like to talk to you about special designed math problems that I created, because through these math problems, I'd like to teach students actually something about astronomy. And I want to start out with telling you why I'm doing that. Here you see a map of Germany with the 16 German federal states. The green states are the ones that actually teach astronomy as a separate subject, but only in grade 10. The yellow ones are the states that have astronomy incorporated into the physics or science curriculum in grade 10. And the red states are the ones that don't teach astronomy at all. And it means some students leave school without having even a basic knowledge about the universe or the things they see in the sky. And I thought that needed to change. Mathematics, however, is a subject that is taught in every grade because it's mandatory. And in mathematics lessons, students encountered two different kinds of math problems. The first ones are what I call technical math problems. They are there to practice a solution method and to train it. You can identify them by words like determine, calculate, draw, fill in. And then there are so-called word problems or applied problems. They are the ones that actually tell a story that the students have to break down and find the math behind it and solve it. And these stories, of course, have a topic that go with it. These topics are more or less from the real world. Sadly, they often are quite artificial, not so much from the real world, but there's a variety of topics. You can see it in this chart. I analyzed 24 math textbooks and read all their applied math problems and categorized the topics. And these are the 19 categories I found. The winner is architecture as your most used topic in these problems. And well, you could say the loser or the least used topic is astronomy. So there I saw my chance to fill in a gap. And also the timing was just right, because in the year 2000, or then after publication 2001, Germany suffered what we call the PISA shock, because we were below average in all of the tested categories. And as a consequence of that, the German educational ministers of the states decided we need to implement national education standards, which means they should ensure that certain competences, not contents, but competences will be taught in every one of our states. So these competence aims for mathematics were published in 2003. Then it took another 10 years to implement them in newly developed math curricula of the individual states. And now it's, well, almost 20 years later, but we are still missing material for the new mathematic lessons or the new demands they have for our current mathematic lessons. So Germany is in need of new math material anyways. So how do I go about when I develop these kind of problems? Well, first I have to think about what astronomical topic I would use. I often get my inspiration from media, things I see in TV. Then I decide what I want to use, a fact, which I define, as a one-sentence truth, like the moon moves away from Earth 4 centimeters a year. Or do I want to use a data set, or do I want to use a physical law? Then I think about with what learning area and for what grade I could combine that. And often I realized that the real physics math and school math clash, because physics laws and physics math, they are way more complex than what we teach kids in school. So there are often unknown units, very small, very large numbers, which therefore are expressed in powers of 10. They're power laws, fraction terms. Long equations with more than one variable. So all of this then needs to be simplified. When I've done that, I, in my case, have to think about what competence can I train with that. I also have to decide if the problem should be closed or open, not just open-ended, meaning there could be more than one solution, but open could also mean there is one solution, but there could be many ways how to get to that solution. And then I also provide a sample solution and a teacher's commentary, to reduce any reservation a teacher could have. Because, not every math teacher is also an astronomy teacher. And I want to show you two examples now, one from grade 5-6, Mars Ancient Ocean, and one for grade 7 and 8, Hubble's Law. And I'm going to switch my screens for that. In this first example, I want to convey one fact. Mars may have had an ocean. And so the introduction is rather small because, there's not much more to know about that. Mars is a planet, that's what it says. And then they have this map of what Mars may have looked like back in the days when there was an ocean. And the actual task are these 3 lines here. The task is to find out the size of the ocean, meaning the surface area, and then also compare it to the oceans of our Earth. So there's one solution, but it's still an open problem because there are many ways to get to that solution. They can either draw in the map, make equal shapes, and then count how many are blue. They could also cut the map up and rearrange it into a rectangle or other box shape and, see what percentage then is blue. And then they will find it out. And since they have to work with this map a lot, I really think they will remember that one fact after solving this math problem. The other example, the Hubble law, is a little bit more complicated because here I'm using a physics law. And prior, they need to understand a whole concept, basically the concept of the expanding universe. So here for you, I've highlighted in orange. These are the things I'm actually going to tell them beforehand. It's about the expanding universe, what the recession velocity is, who Edwin Hubble was, and also that's Hubble's diagram, that he saw a linear relation there, but this linearity actually only is valid or is only a good estimate up to a distance of 400 megaparsec. A stumble stone could be the unit megaparsec because they don't know that. So here I gave them a little box that explains to them how far away a megaparsec is, comparing it to the distance from Earth to Sun. I also already gave them the actual function in mathematical terms and told them this, HO is actually called Hubble parameter. What I didn't tell them here in this introduction is what the Hubble law itself actually is or what it means. That's what I think they should find out by themselves by interpreting this graph. And that's what they do here in subproblem B. They have boxes and they need to check if they're right. And if not, they have to correct them. And if you look here at the dark blue one, it says the further away a galaxy is from us, the slower it moves away from us. That's of course wrong. We can have a look at the graph. The further away, of course, the faster the galaxies move away from us. Speed is also increasing. Then there's another subproblem, which gives them even more truth about the Hubble law. It tells them that the Hubble parameter is not, this one value because different measuring methods actually come up with slightly different values, but a common used one is the 72 kilometers per second per megaparsec. That's also a connotation I decided to use because here you can see, in the top part there actually is a velocity and here's the distance. And in the next subproblem, they will learn a minimum value and a maximum value for this Hubble parameter. And there's also another one where they have to interpret the graph. And I'm really a big fan of these kinds of problems because that's but I actually understand what mathematics is for. It's not just, you know, about the technical working, you know, find this point or calculate the slope or whatever, but really try to get what the graph is actually telling you. So if you have a look at this third line here, it says the galaxy I'm in is not moving through the expansion of the universe from my point of view. Can I see that in a mathematical model? Yes, I can, and I can tell by the point 0, 0, because it's the point of this linear graph. So now you've seen two of my examples. The first one, we only talked about conveying one fact, and the second one was, you know, conveying a law, which means you actually have to convey a lot of facts. Is a little bit more complicated, but when you design the subproblems in such a way that, you know, it always comes back to focusing on the law itself, then I think students will get the main idea as well and remember that. The other problems that I've created belong to one of the 5 categories. It's either about exoplanets or it's basic knowledge, like our solar system. It's about space ventures, black holes, or cosmology. If you are interested in getting the problems, if you have any questions, you can either ask today or you can also always write me an email. Thank you so much for joining.